So I think we should go ahead and start. I just want to double check that all our three speakers are still here.
Yeah, I'm here.
Yeah, I'm also here.
I'm here too.
Perfect, perfect. Okay, so welcome to our first webinar in a webinar series that we are planning to start, or we actually started this year for our committee ABJ 70, the Committee on Artificial Intelligence and Advanced Computing Applications with the TRB. So the webinar today is with the title of TRANSFOR19 Results and Lessons Learned. As a brief overview, TRANSFOR19 was a data competition that was organized jointly by our committee and the IEEE Intelligent Transportation Systems Society, and was sponsored by DD. The competition was focusing on coming up with, a fast and intelligent or advanced ways to predict speeds using trajectory or vehicle trajectory data that was acquired or collected in China. We selected, or the committee selected, 5 finalists that presented their work at the TRB meeting in a workshop that was organized by the committee. And we ranked them. Today we will have 3 of those 5. And those are Dr. Ji Sun from University of California, Irvine, who got the first place in the competition, and Dr. Toon Bogertz from University of Diutsu, who came in the 3rd place, and Dr. Pranamish Chakraborty from Iowa State University, and he came in the 5th place. So the way the webinar will go, we will have all presentations back-to-back, 20 to 25 minutes. And if you have any questions, just send them in a chat box. Please make sure you keep yourselves muted all the time. And if you have questions, send them in the chat box and we'll read them to the presenters at the end of the webinar. Without further ado, we'll have our first presenter, Dr. Z. Please go ahead.
Yeah. Right. Can you guys see my screen? Okay. My name is Ji. My name is Zhe Sun. I go by Jared. I'm the system manager at Institute of Transportation Studies at UC Irvine. So our team won the first place in the TRANSFOR19 data competition. And today's presentation is basically a recap of our winning model, as well as some of the lessons we learned from this competition. Just as the title says, less is more. So first of all, let me introduce my all of the team members. We have, besides me, we have the other 4 wonderful team members, Yiqiao Li, Pritik Malik, Lu Xu, and Dr. Qinglong Yan. So three of them are still current PhD students here, and Dr. Yan graduated recently. He's working at Streetlight Data as a data scientist. So here is you can see a chart of the performance of the data. Our model actually achieved the highest prediction accuracy among all. We were actually leading by a pretty large margin, and this could not have been possible without the teamwork. So let me start with the description of the data. So the data set was provided by DD. It's a bunch of GPS vehicle trajectories on the day of December the 1st, 2016. And inside the data set, we were provided with longitude, latitude, driver ID, order ID, and timestamps. And for each of the, so each of the order is actually, so for each of the driver can take actually multiple orders, and each order is actually a complete trajectory with a start point and end point. And here is just a plot of some of the randomly selected trips. And the starting area is shown in the right rectangle here. Is a 2-way street, which is about 800 meters long. So we were asked to predict the speed on this single day for time periods between 6 to 11 a.m. and 4 to 7 p.m. And here is just a plot of the speed which were provided. The blue line are the northbound speed, and the orange line are the southbound speed. So our mission was basically to fill the gaps in here based on the speed estimates. And so we started with data pre-processing. The first question we try to answer is, how do we get a speed estimate from GPS? How do we get like a starting point? So we first resample the trajectory based on uniform time intervals. The original GPS points are 2 to 4 seconds away, so we resample them to have so that they can have a uniform time intervals, and then we calculate the instantaneous time speed for each of the points based on this equation. So this is basically the travel distance divided by the time difference, and then for each of the GPS points, we calculate a so-called bearing, which is the angle between the travel directions and the true north. And we use this threshold to determine northbound travel or southbound travel. For example, if the bearing is between 185 to 225, then it's traveling southbound. So here is just a recap of how we did the data pre-processing. So with the GPS data, we first resample them so that they have uniform intervals, and then we calculate the speed, instantaneous speed, and bearing for each of the time points. And in the end, for the speed at time t for direction d, the average speed for it's just calculated using this equation. So this basically says we want to take the average of the speed for all the vehicles within the starting area that travels the same directions. And imagine that you will do the same process again and again for each time step, and eventually you will get a time series of all the speed. And then we move on to fill the missing values and then do some smoothing with spline functions. And so we call this time series of data a naive speed estimate. And then the second question we try to answer is, how do we actually improve this naive estimate? So here is just the plot of our naive estimate versus the observed speed. You can see they are actually pretty close. The root mean square error is 6.936 for northbound and 8.832 for southbound. But can we do more? Can we make them even closer? So the idea is to assume there is a time-dependent relation between the ground truth speed and the naive speed estimate, and then we can use one of the machine learning approach, which takes the timestamp and the naive speed estimate as a feature in order to estimate the final observed speed. So the natural choice will be the artificial neural network, where because based on the universal approximation theorem, the artificial neural network can approximate virtually any functional form given enough parameters, right? Here is just a list of the neural networks that's being used, and you can see how many parameters has been used just to achieve the task. Well, in our case, we started with two small neural networks, just because the sample size is really small. We have only about 160 data points. So the model 1 is a neural network with 2 layers and 20 neurons for each layer. So we have totally about 501 parameters. For model 2, we have 481 parameters. So both models have almost a similar size, but the model 1 is a bit shallow, but it's wide. The second model is a bit deep, but it's narrower. And then to choose the best model for each directions, we use the five-fold cross-validations. So basically, you split the data set randomly into 5 different sets, and every time you train a model on 4 sets of the data and test it on the remaining 1 set, and you will repeat the process for all of the 5 sets, and eventually each set of the data will be used exactly once as a test set. And then we calculate the so-called auto-fold MSE for both directions to do model selections. And looks like the shallow model works better for the northbound, and the deeper model works better for the southbound. And due to the small size of the sample size, due to the small size of the training set, it's very easy to run into overfitting issues. So we adopted the so-called model averaging technique. It's an ensemble method. So basically, for each of the sample data set, we train the same neural network for 30 different times with different initial values, and we take the average of all the ensemble as the final result. So the reasoning behind this is the so-called Biasvariance trade-off. The total MSE can be partitioned into bias plus variance plus irreducible residuals. And as for a neural network, as the training goes on, the model bias actually decreases, while the variance increase. And ideally, we want to reach we want to reach a point where the sum of both reaches the minimum, which is here. But in practical, it's very hard. And one of the common issues is overfitting, where when you go too far away. And but when you do model averaging, the bias is actually unchanged. And since you are averaging across multiple models, you basically reduce the variance. So the overall MSE will be reduced, and also the risk of overfitting is lessened. So we didn't stop there. We also did a model comparison with. We also compared another classical statistical model for prediction. That is the Array-Max model, autoregressive integrated moving average with exogenous variables. Well, in this case, the exogenous variables is the naive speed estimate, and for these directions, we choose we plot the ACF and PACF and use other techniques to pick the best model. And so eventually, we use the Array-Max 100 for northbound, Array-Max 013 for southbound. So these 3 digits represent the autoregressive term, integrated term, and moving average terms. And here is just the results comparisons between all these models. And this is the result for the neural network. You can see that let me explain. The blue line is our speed prediction results, and the orange line is the observed speed. And you can see that after applying the neural network on top of the naive estimate, we reduce the RMSE further from 6.963 to 6.052 for northbound. And for southbound, it works even better. We can reduce the RMSE from 8.8 to 5.3. And here's the result for the Array-Max model. For the Array-Max model, we achieve even better results. The Array-Max model reduced the total RMSE from 6.9 to 4.4, and 8.8 to 3.8 for the southbound. So this is 6.5 here for neural network and 4.3 here for Array-Max model. Does that mean we have to use Array-Max model for the predictions? Well, the answer is no, because remember, these RMSE are actually calculated based on the overall, based on your training set. So it just indicates how well your model fits your training data. It doesn't say anything about how the model generalizes with the additional data. So again, we used the cross-validation method to do a model comparison. So basically, so this is the way we split the data set, where the blue part is the training set and the orange part is the testing set. So we consider 3 different scenarios where the testing set is in the morning, in the afternoon, or in the evening. And we calculated the RMSE for each of the training set at different time period. And actually, the overall RMSE is here, and the neural network has actually the lowest RMSE than Array-Max model. That's the reason we choose the ensemble neural network in the end. Actually, if you go back a little bit to see the results of this Array-Max model, you see that the behavior for the Array-Max model in the southbound in the afternoon is pretty weird. I mean, once you see a pretty sharp drop when you have observed speed, but it just flows. It stays almost in the same level when there's no observed data. So it's actually an indication that your model doesn't generalize well. It fits pretty good with your original data, but when there's no training set, it's just it's not following the trend. So just some of the takeaways for this presentation. So machine learning method is very powerful, but it's not the silver bullet. Basically, when you deal with a small sample size, overfitting becomes much harder to avoid, especially for a small sample size, because for machine learning models, it's really quite complicated, and there are many parameters involved, and it will be very easy for your model to capture the noise, not only the trend, but also the noise in your data. So you will go overfitting. And also, a multi-layer strategy is still the best approach. Just like it's a good approach for cold weathers. In this approach, we started with the naive speed estimates, and then we further improve the results using a neural network. So I would say that the neural network will not bring you all the way from the starting point to the end point. You have to start with some mathematical or physical models, and the machine learning method will probably help you to cover the final few miles, but it won't bring you all the way from starting point to the end point. And the third thing is the any model is just as good as the data flows in it. In this case, we have a pretty good naive estimate to start with. That's why our final model can achieve such good accuracy. And in the general case, if your data is not as clean or if your model is not as accurate tagged, then your model will suffer. In addition, if you need to ensure the right variables are, in addition, you need to ensure that the right variables are being fed into the model in order to achieve the best results. That's pretty much of what I want to cover today. And here is my contact and my LinkedIn. So just feel free to ask me any questions if you have any, and I will be able to answer questions at the end of this webinar. Thank you.
Thanks a lot, Dr. G. Much appreciated. Like I mentioned, you can either send your questions in the chat box, or as Dr. G mentioned, you can email him directly. Now we're going to go with the second presenter, Dr. Toon. Please go ahead.
Okay, if I think everyone can hear me. If not, I think someone will remind me. So I'm Tom Bogart. I work for Tech Mobility in Spain. And basically, we were third in the competition, but we made some mistakes in our model, which I will explain later. But we come from a complex approach to be applied on a pretty simple. I'll explain. Wait. Oh, wait, my presentation is not working. Okay. So first, I will do a small introduction on why what the complex model is actually deep learning. So where deep learning is. Then the methodology of the entire approach, going from the GPS traces to our predictions. Then I will go over our new results, and I will end with the conclusion and what we're working on now. So basically, yeah, why we do traffic forecasting, I think everyone knows it's to contribute to ITS, or intelligent transport systems. So we now can use data-driven models, and in history, usually statistical models were used. With the availability of nowadays the data sets growing and the collecting of data is getting higher, we can actually use deep learning methods to improve the performance. So where is deep learning situated? You have artificial intelligence, which tries to mimic human behavior. Then you have machine learning, which is trying to learn a machine to do a certain thing. And then you have deep learning. Deep learning is actually a subset of machine learning, which uses a lot of linear equations, but in a lot of repetitions and a lot in parallel to detect more complex patterns. And so what's the big difference between conventional machine learning and deep learning methods is actually that machine learning methods are based on human logic. So basically you can use the same logic in machine learning, or there is some logic that you can understand. and they don't need a lot of data to achieve their top performance. The downside of these methods is that they have difficulties identifying in traffic. You have spatial data, which means how far two data points are apart in coordinates. And these traditional methods have difficulties detecting them. Also, the scalability, using them on a larger scale, is more difficult. And the missing data and noisy data can disturb the model's predictions. And then you have deep learning methods. So basically, they have the advantage of being able to catch spatial and temporal components, and they're easy to scale. But the downside is that they're pretty hard to understand in what's going on in the model. And you need a lot more computational power because the models are more complex to do these complex pattern recognitions. And they also scale with the amount of data you have available. So more data will mean more accurate predictions. So now, what are the gaps with the deep learning applied to traffic forecasting? You can see that actually it's a trend that only started to become more relevant in latest years. This is because of the data that's acquired and the computational power that's available. But basically, we detected that the scalability, so basically the models are only used on small scale or are used in really complex, unscalable ways. And the efficiency of training is linked to the complexity of the model. And also detecting the spatial and the temporal relations in traffic is actually a difficult matter in deep learning. And then you also have less or not a lot of models that are capable of doing long-term predictions and predict for an entire network wide or an entire city at once. Usually they're focused on small regions. And of course, there is always an issue with missing and errors data or error data in GPS data. So how did we approach this problem? First, we looked, first a small difference again about the deep learning and machine learning, which is basically you need to give the features in machine learning to get a prediction, but deep learning is more complex, so it needs more parameters, which is a downside, but it can detect which inputs it needs to create the output. So we started with looking at the data. This is just one day of data in Xi'an City. And you can see that there's actually not a lot of points at this time during the night. And also the smaller roads, I think people are starting to wake up around now, so we will get busier. And you can see that the smaller roads have less measurements, and most measurements are actually located on the main highways. This is something we take into account in the following steps in our process. And you can basically see the red points is where there is a lot of congestion, and and there is a nice square box where the routes ends, and this is because data provided them in this format. So this is something we also need to take into account. All right, so the road to our predictions. Basically, we start with map matching. Every step will go into detail in the following slides. So the first four blocks are for pre-processing of the data. This will be done and then we split up in two branches. So we made a model which is capable of predicting for one individual segment. So this would be the northbound segment or the southbound segment. But we expanded our model to be able to predict on a network-wide scale at the same time. So it can predict for the entire network at one time step. Then there's an abstraction of this process that you can follow in the following slides. So first, the map matching. Of course, with GPS data, you're not 100% sure on which roads they are. The data set of Didi is pretty accurate, so basically the map matching didn't really influence a lot. But from this method, we get individual entries. So we know at this road we have a measured guard with an average speed of something. Then we combine those entries. So basically we combine per road in the entire city. For example, at 8 we have an average of 60 kilometers an hour, and we have 12 measured cars. And in this way, we have a structured data set for each road in the entire city. So you can see the dimensions being pretty high, 5,500 by 2 features. The 2 features are the average speed and the number of cars. And then you have 17,000, which are the amount of 5 minutes in 2 months, because one time step is 5 minutes, which is the same for the data competition. Then we fill in the missing values. We know if the data, if there's only 2 missing values, we know it's going to be pretty close to the 2 first encountered values. So there we use interpolation. If the values are missing more, or if there's a bigger gap, we use an average imputation. So if it's 2 at night at a Monday, we will look at every 2 at night on a Monday in the training set to fill in the average values of this training set. Next, like I said, the smaller roads have less influence or less measurements or are less reliable. So we actually remove all the really small roads that have unreliable data or just not a lot of measurements, because this will confuse our model or will make it more complex to learn patterns. So we will keep only the primary and secondary roads to identify the traffic situation in the entire network. So now we will split. The first thing is a data reduction for the single link predictions. We still have too much information to efficiently train a model on. So we're going to remove more information, but it's always removing information is a trade-off between efficiency and the loss of information. So we investigated 3 approaches. So basically the first general approach, which is correlation, is just looking at a street and looking at all the other streets and see if they follow the same trend. And basically if you have a high correlation, the ones with high correlation are indicated in red. We select 100 streets to predict for 1 street. So basically we look at the traffic situation at 100 streets to predict for the green street, which is in the middle. And then we developed, actually, we thought the correlation is not really what we want to use, because we use the last 5 time steps to predict 1 in the future. So if we take the total correlation over the last 5 time steps, compared to the first in the future time step, we actually get a different selection. You can see that the streets are different. So basically, this is the first new implementation in our model. And then we compare it to what's standard or used to be used in traffic forecasting, which is ingoing and outgoing. So basically, you just look at the traffic that's going in and you look at the traffic that's going out. And that's basically the only thing you consider to predict for the green street in the middle. So now that we selected those streets, you saw that this is a graph structure, which is unable to be processed by a deep neural network. So we need to translate this network to something that can be processed by a deep neural network. So we do this using adjacency matrices. Basically, if you have it's a square structure which translates a network to a square matrix. So you can see if there is a connection between 2 nodes, it will become white. And if there is multiple streets between the same nodes, there will be 2 on both sides of the diagonal will be an indication that there's a connection. And we will translate, instead of having only 0s and 1s, we will translate this to the average speed and the number of cars measured. So this is a zoom in of how it looks like. And then if we create a matrix, we actually lost the distance between the streets, because we don't know if the 2 nodes are close together or not. So what we did is we sorted the nodes in the columns and in the rows to their longitude and latitude to reintroduce the spatial feature. So finally, we approach our deep neural network. And basically, the deep neural network takes into account the last 5 time steps, like I mentioned before, in graph structure. The graph structure actually is just 2 adjacency matrices, one for the average speed of all the cars that were indicated in red, and the other one, the number of cars. We use a convolutional model to extract the spatial features. So basically, we try to extract distances, how close are they related, to translate them into a tensor which contains the information of clusters in the city that are representative for the road to predict. Once we have the spatial features, we stack them in time. So we first extract the spatial feature of time 0, then of 1, then of 2 and 3 or 5. And then we process them in time to look for relations in time. So if we find them, we use an LSTM, which extracts if there's temporal features, and they will be indicated. And lastly, we use a feed-forward neural network to combine all those features and make our prediction. There's one more comment that a lot of literature says that it's not good, but we found it's actually applicable in traffic forecasting, which is using activation function in regression applications. So basically, you can see the orange distribution, which is a linear distribution. So if you have an input of 0.5, your output will be 0.5. And then we use a sigmoid. The sigmoid redistributes the distribution to a broader spectrum, so the model has more room to make changes. So why would this be bad? The thing is, if you use a sigmoid function on the activation function, as an activation function on your output, you're not able to predict 0 or 1. So you're basically limited between 0 and 1. So this means in terms of traffic forecasting, you're unable to predict below the minimum value in your training set or above the maximum value in your training set. But if you think about traffic forecasting, the minimum value is 0 kilometers an hour, and the maximum is the maximum allowed speed on that road. So basically, we know the domain to predict for, and that's why we use a sigmoid function to allow the model to be more accurate. Now we split up. So this is actually something we made after the competition. And our models was too complex. So basically, the first speaker was completely correct with saying simple is the best. And we used a too complex model to predict for one street, but we used our same model to predict for the entire city. So instead of making our model easier, we made the problem more complex. So now that we do this, we actually look sort of like the same with the time correlation. We try to encode the city or get the most significant streets to represent the state of the city. We do this again, including time. So we use the last 5 time steps to try and auto-encode the entire city in the next time step. If we train this model on all the data we have, we can extract the most influential streets of the city. And this is the result. You can see that the coverage is actually pretty good. There's everywhere in the city, there's a street that represents the local traffic situation. So the second step in this process is again creating the adjacency matrix. To give a better example what these matrices are actually like, I did a double zoom on the matrix. And then you can see at night it's more light because the average speed is faster during the night than during the peak hours at 12:30 or at 8:30. We also only consider average speed because this will reduce the complexity of our model. So the model itself is actually based on the model we used for the single link prediction because it was already a complex model. We use the last 5 time steps, we predict, and then we actually reconstruct the prediction back to an adjacency matrix, and we just predict again. This is so we use our model in recurrent fashion to actually be able to also predict in time. So we don't only predict for 5 minutes, but we also predict up to 1 hour, up to 3 hours, and this is also done for the single link model. So we made the problem more complex, being that we can predict over the entire city, and we can predict on longer time horizons than 5 minutes. So the last part in this model is if you can predict for the roads that are representing the traffic situation, to actually decode those roads to present the entire traffic situation. How do we evaluate everything? Is basically we use RMSE, the MSE, the MIE, and MIPE, which are the regular ones used in deep learning. But we use 3 different versions. So basically this graph indicates the amount of measurements we have over 1 week aggregated over the entire city. And you can see at night there's a lot less measurements. So basically it's not reliable data. To force the model to focus during the day, we use a weighted version, which is actually pushing makes the errors made during the night less significant. We also use a Friedman's test and a post hoc probability Holmes evaluation to make sure nothing is due to randomness. We also expanded the streets to indicate more streets to be able to see the generalization of our model and being able to predict on different speed profiles. So the green ones are the ones used in the competition. And we also did the same for the Chengdu city. So basically we expanded to another city as well to make 100% sure our results are correct. So what actually did we achieve? So for short term, the time correlation is one of the first things we did. So now you can also see we predict up to 4 hours in intervals of 5. So we predict 4 hours at once with intervals of 5. But for short term, it's actually not important to have a lot of information. If you know the street itself, the information that's happened on the street, it's not that important for short term. But for long term, it becomes more important to know the situation of the entire city or what's more farther away and what key roads are. So now the single link prediction is actually the one that we used in the competition. We also expanded from, instead of 1 testing day, we did an entire week of testing. That's why you have multiple repetitions. we created a model using the sigmoid function, which is all extraordinary as well, with our suggested pre-processing. And basically, we improved our model significantly, but and this we actually made a lot of mistakes, because during the prediction day of the competition, a lot of routes were erased during those 2 hours, which go through the 2 streets. And as we didn't take that into account, our model was really confused during the prediction time. So what are our predictions? You can see the orange one, which is a 5-minute prediction, so it looks pretty accurate. And the green one is if you predict 4 hours in the future. So the general trend is still observed, but some of the specific instances are not detected. So it's not over time, our performance goes down a little bit, but still is able to predict. So if we recalculate in the windows that were predicted for the competition, so we use 7 days of the last 7 days of November, and we use the same time slots on every day, our model is actually improved to be to have an error of 2.34 averagely over the 2 segments. So basically, we're capable of increasing our performance, and we also tested on a longer testing set. So we expanded this to a network-wide level. The network-wide level averagely, as we would evaluate it the same as a competition, had an average rating of 3.2, and that's in the same manner of the competition, so it's in the same intervals over the entire city, and shorter meaning 5-minute prediction. So basically, we can predict over the entire city. With on the outskirts, we experience some problems, but this is also because Didi provides a perfect square. So some of the streets on the edge are with confusing data and a lot of missing data. We can keep this performance up to 1 hour, but some flaws show up if we train a model for longer than 1 hour. So it looks, this is a little bit more statistics about the network-wide predictions. So you can see the histogram of the weighted RMSE, which is the RMSE that has been optimized for. You can see on both ends, there's some distribution, or some bins are on the outer extremes. So in the top right corner, you can see an average prediction. So this is an average prediction in the city. And on the left bottom corner, you can see the prediction with the largest error. So basically, this comes from the fact that there's not enough data in the street, and it creates a lot of noise because of our imputation method, looking for the average over the entire training set. And actually, this noise gets repeated because there's too many missing values. And then the other extreme is on the right bottom corner. And this is where there's only one measurement in the street. So basically, our last resort of imputation is to just interpolate. And this can result in a straight line. And the model is able to just learn a straight line to have a perfect prediction. But because they're on both outer ends, it doesn't really influence the distribution of our weighted RMSE. So what's the relation between the missing values and our performance? Is actually we look at the performance and we can say that we are able to predict accurately if there's less than 35% missing value. So if you have 65% of the time intervals having data, we are capable of predicting in pretty accurate manner. This is the fact, so we can keep performance to 1 hour. As you can see, the top two images are the same segment in different times, and the bottom two is also the same segment. So basically, these are random segments in the city because we predict over the entire city at the same time. The flaws that I was speaking about, if you go to higher time horizons or longer time horizons, are actually the squaring of the signal. This is due to error propagation, and we're actually working to fix this at this moment. Yeah, so this is also to explain the error propagation. We have 3 versions of the network-wide model to predict for network-wide, and you can see after 100 epochs of training, it's actually still learning. So basically, if we allow it to learn longer, it will be able to maybe increase in performance. So what is the conclusion we can draw from our methodology? Is actually that we have created some efficient data reduction structure for GPS data. Also, we introduced the idea of time-based correlation, which improved the performance not only of our models, but we also tested it on LSTMs, on KNNs, on SVMs, and basically all performance increased. The suggested models are capable of doing accurate predictions both on long term and on short term. And we also created one, because it's true that we have a complex model which has 14 million trainable parameters, but we created a version of this model which only has 4 million parameters, which is not a lot for deep learning. And this model actually has also pretty good performance, so it will be applicable in situations where there's less computational power available. So yeah, the model that we used for single link predictions and the 5 minutes, so only short-term single link, is the one that got third place in the transfer competition. The other models are not used in the competition. So basically we improved our performance. So for the network-wide, which is the second part we did, we created again a pre-processing to represent the traffic situation of a city. And then we are capable of predicting accurately for short term up to 1 hour. And we can do pretty accurate predictions for the entire city at the same time. The best performance is measured if there's less than 35% missing values. And the training time of these models is actually comparable to the training time we have with single link models. So basically the efficiency of training, if you compare to the amount of predictions you get, is a lot higher with the network-wide models. Finally, the future work, or what we still want to improve, is the efficiency of the convolution. So basically, there's some things with adjacency matrices containing a lot of zeros, and we want to fix or reduce the training in those parts of the model. We want to use transfer learning if we do the single link predictions, and we want to reduce increase the time steps if we are applying long-term predictions. So it doesn't make sense to predict every 5 minutes if you go up to 4 hours. And then we also want to test our model to non-recurrent events, because basically we predict in function of the state of traffic in the entire city. So basically we predict in function of other streets. So we think it's less prone to non-recurrent events. So if you want any questions outside of this webinar, you can also contact me on my email, which is now on screen. And I will also be here at the end of the webinar to answer all your questions. Thank you.
Great, thank you so much, Dr. Toon. Great presentation, of course, and the competition spirit is there. So we're gonna go forward with our third speaker, Dr. Pranamish. Please go ahead, and you already shared your screen. Perfect.
Yeah, thank you, Dr. Osman. So my name is Pranamish. I'm a pre-doctoral research fellow in Iowa State University. And the topic of this presentation is traffic speed forecasting using a hybrid LSTM approach. I would like to thank all my members of this team, who was Shubhadipto Shua, who had actually this model prepared for his dissertation. And right now he has graduated and working in NVIDIA, and also my other colleagues, Archana Tong, and our advisor, Dr. Anuj Sharma from Iowa State. So as we are basically talking about like traffic forecasting, so just a brief introduction. We have been talking for this like quite some time right now, but if we want to divide like traffic forecasting, it can be divided into like two parts, which is short-term forecasting and basically like long-term forecasting. So in short-term forecasting, you're basically looking for like what happens like 10 minutes, 15 minutes, or like 1 hour, or it can go sometimes up to like 3-4 hours. Similar to what we have in the competition, or something like predicting what will happen during the morning peak hours or evening peak hours or something like that. But also another one can be like a long-term forecasting, where we have to basically predict for a much longer duration. So something like what will happen over the next day, or what will happen over the entire next week, or something like that. In this study, we are basically focusing into the short-term forecasting. And I will basically go through like how we are doing that, and like what's the prediction window that we are having. We can have like different prediction windows. The transfer competition basically was looking for just the morning peak and the evening peak duration, but it can be just a simple like a 10 minutes or like 1 hour prediction window. So what are the key factors that can affect the traffic forecasting? So one of the main factors is obviously how the traffic has behaved over the past. So using all the historical data. So when we have like regular congestion, we know that during the peak hours, when the peak hours start, if we can get a pretty good estimate from the historical data, then we know that, okay, so possibly like typically in the US, it's something like from 3 p.m. or 3:30 p.m. the evening peak starts on. So using all this historical data, we can get a very good knowledge of like how the traffic is expected to be behavior. And that will this is basically the key factor, the basic key factor for going for like traffic forecasting issues. But we have a multiple other factors that can be also, that should be also taken into account for going like even better estimates, particularly when conditions are not exactly what has happened over the past history. So something like if a work zone has started, so if we know that over the last 2 weeks or 3 weeks, there has been a work zone that's going on, that will possibly obviously affect your traffic speeds. And that we need to take into account so that we can have a better forecasting model in our approach. And finally, when the weather hits or something like that, we often happens in Iowa, where we have a like lot of snow, or even it can happen with like heavy rain or any other bad weather conditions, where we know that that can affect our traffic speeds. And one of the best approaches of using all this thing is getting all this information. So something like if we know that the work zone is going on, or if we can get from the weather forecast that the bad weather is coming to affect the traffic, then we can basically help our traffic estimation to become like much better. But then we completely have the non-recurring things, something like crashes. So when the incidents or crashes are happening, that can affect our speeds, what is going to happen, and that will be obviously affecting how our forecast model should be. So our typical forecast model should take into account like all these factors. or something like when a crash has happened, it should take into account, so okay, so the crash has started. It cannot possibly predict like the crash, but once the crash has started, then it's something like, okay, so over the next 15 minutes or like 30 minutes, there is obviously going to be like heavy congestion, because that's what has happened over the last 5 minutes or something like that. So how typically traffic forecasting is being solved is basically divided into like two classes. So something like traditional statistical models, where we basically use something like the first presentation has also looked into that with something like ARIMA models, or it can be also used in the traffic flow theory, where you are basically using all the fundamentals of the traffic flow and how the traffic is expected to behave to come into conditions of how traffic will behave during the short time. But also it can be something like Kalman filters. But with the recent advancement in machine learning algorithms, what we are seeing is like there has been a lot of models that are coming in, which are using just the data to get to very good forecasting models. And the machine learning models can be typically divided into like two parts, where you have the classical models, or something like a shallow models that we say nowadays, which are basically regression models that we do, which are not too much data hungry, I would say. But with the recent advancement of all this deep learning that has come into like computer vision and all the like the speech recognition and all these things, so that has been started to get into a lot of application into our traffic domain and also into traffic forecasting. So in this study, we are basically started off with a LSTM model, which is basically one of the main models that has been used for all this forecasting. So it started off with like speech recognition things, and then it basically advanced into the typical forecasting things. But it has been around for quite some time. Just with the addition of a lot of data that we get, we are basically getting like good results in different fields nowadays, and that's why this is basically getting like so popular these days. But what it typically takes into is something like a simple recurrent neural network. So that will be basically taking into like what is happening just on the past, and basically putting that information forward to predict like what is going to happen. But the typical neural network model has the disadvantage that it cannot basically remember the long-term histories. And that's where the LSTM comes into, but it basically takes into consideration the long-term things into its memory. So it's something like it takes the predictions into the copy and basically tries to remember what needs to be remembered. So something like a PM peak, when the PM peak is happening or when the morning peak is happening, take all this into the memory and forget the remaining things that do not need to be affecting the model accuracy. And then we basically select which features are important, and we ignore the remaining features to basically get our final model that can be basically used for forecasting. So our basic thing, what we did was something like, which is traditionally called very classical, something like transfer learning. And this has been one of the basic advantage that has been shown in like different applications of like deep learning things, where we basically, one of the basic advantage that has been shown over the recent 4 or 5 years is, obviously we know that the deep learning is like basically very data hungry, where you need a lot of training data to basically build your model. But what has been shown, and it started off with computer vision basically, where you basically learn from a very intense data intensive model. You learn your basic model, but with that basic model, once you learn the weights, you know that some of the things will transfer well. So something like when we are basically trying to learn something like cars, it basically knows that, okay, so a car consists of like a wheel or something like that. But then basically when we want to also detect like trucks, we know that some of the features are still going to be important that we have learned over our massive data set of cars detection. So that's what transfer learning will be doing. Is it will basically learn from a even better or even more data intensive structure that we have to learn, like how the entire thing basically performs, and then it basically tweaks that model to basically fine tunes it to our final model. So something like when we are basically have a much wider data source or much larger data source of traffic data available, we are basically trying to learn how traffic behaves. So something like it will try to learn when that there is something like a morning peak or evening peaks that happens, and that will happen like irrespective of the location that you have. And with that learn model, once you get into a smaller data source, you try to learn what are the new things that are there with already learned things that you have learned over the past. So and that's the main thing that we are using here. So something like transfer learning to basically learn first our model on a much more data intensive structure, and then transfer it to a transfer competition structure. So our objective here is to basically first build a hybrid LSTM model, and then use a transfer learning, which can, and we apply that model to a completely different data set, completely different locations, and we try to see that how well still it performs. And we then obviously compare the performance with some of the very baseline algorithms to see how it performs with all the very traditional algorithms that have been used constantly over the past for traffic forecasting problems. So our data set was like, we had like 2 different data sets that we are using here. As we said, like for transfer learning, we first had to train on a much larger data set, and that's what we are doing here. So we first had our Des Moines data set. So this is basically, Des Moines is the capital city of Iowa, and it has the most traffic congestion over the Iowa. Iowa doesn't have like too much traffic congestion, but all the traffic congestions are like typical morning peak, evening peaks do happen a lot in this region. And that's what we are taking here. So this is a part of the interstate I-235. And we took basically like 15 sensors, which are basically radar-based sensors. And we are basically using the traffic data from there. And finally, whatever we have learned from this Des Moines data, we are applying into our TRANSFOR19 competition data set, which was the Xi'an City data set that has been also covered with all the other speakers. But what it basically had is something like they had a basic test segment where we needed to predict the traffic speed. And we basically had all the other informations, and we had to basically predict the traffic speed for the test segments. And one of the major difference between these 2 data sets was the first data set is on a freeway data set. So it is on an interstate where you have like free flowing traffic, but the Xi'an City is a complete arterial data set. And we basically want to see that how well the model performs after it has learned from the freeway things, how well it still performs on the arterial data sets. So in the Des Moines data set, we basically, we trained our model. Since we have access to that data set, we trained our model on a much larger data source. So the basic training was done on complete 1 year of data for the 15 sensors. And the validation was done using the 2 months of October and November 2016. And then for the testing, we basically took like 2 days. So the first day was a normal weekday of the 12th December. But we also wanted to see that how well it performs into the inclement conditions. So that's why we took another day, which was the 16th December, where we had a snow and freezing rain combination, which basically affected the traffic a lot. So we basically wanted to test it fully, like how the model is performing on various different conditions, so that we have complete knowledge that our models really don't overfit into a particular conditions. And then we basically transfer that to the Xi'an city, where it's basically, we had 2 months, so October and November, which was basically provided to us. So we took the, we kept out the last 3 days for our validation purpose, and we used the remaining days for our training purpose. And the testing was done on the 1st December, which was the test date as specified by the competition. So the data preparation, coming to the data preparation. So Des Moines dataset, these are basically radar-based sensors. So here we do not get like trajectory information or something like Xi'an City does, Xi'an City dataset had, but rather we are getting the aggregated value of every 20 seconds, what's the volume, what's the speed, and what's the occupancy. So it's basically a very traditional traffic data collection methodology that we had here with the initial frequency of 20 seconds. But then we aggregated into 1 minute, because 20 seconds is like a very small duration with a lot of noises. So we basically aggregated into 1 minute duration frequency, and we then used a moving average smoothing with a 5 minute duration window to basically smoothen out, because all these radar-based sensors are actually very noisy data set that we had. And then the Xi'an City, that has been already covered by other speakers, but it was a completely different data set, which is a vehicle trajectory data set, where the GPS locations were given for the different drivers that were going around that segments with a timestamp and the GPS location. And from that information, we're basically getting the vehicle speed, and we had to aggregate that into 5 minutes duration, similar to what the competition was based on. The initial raw frequency of the GPS trajectories was 2 to 4 seconds. So coming to the model architecture, as we said, we are using a hybrid LSTM. So we are using like 2 parts. So first is what has happened from the start of the day, what has happened, what has been happening to the traffic. So this is basically to get information that what has happened in the recent past. But also we want to include like what has happened over the past history. So that history information will basically give us information of when the congestion has been starting or something like that. Well, the recent information will basically help us to find out, okay, so if something like a incident is happening or a bad weather is hitting, that information is basically taken into account. So something like using the start of the day information. So using all this, what we are basically doing is we have the actual data. So suppose we want to predict for the t+1 second. So we have the data up to the tth second. And then we are basically using the all the history of the last 4 weeks into our account using another LSTM cell. And then we are basically predicting in 1 minute intervals. So for tth minute, we are basically predicting the t+1 minute, and with that prediction, we are now predicting the t+2 minute, and similarly, we are going to like t+nth minute. So n can be whatever we want. It can be something like just a 5 minutes or 15 minutes, to it can go something like a 2 hours, 3 hours, or something like that. So coming to the training of our model. So first, as I said, that we are basically trying to find out how transfer learning works. So we first had our base model learned on the first 3 sensors. And once we learn the model weights on the first 3 sensors, we are basically transferring it to the other sensors. So first to the sensor 1, 2, and 3 are basically now retraining, fine-tuning the learn model basically to learn the sensor 2, 3, and 4, some similarly like sensor 3, 4, and 5. And then finally, with all these models, with the fine-tuned models that we have learned, we are basically averaging the predictions coming from the different models. So something like sensor 2 will have the 3 different models from which the predictions will come, and we are averaging it to get our final prediction, and thereby the final accuracy. And then we are completely transferring it to a complete different location, which was the Xi'an City, which I said as earlier is a arterial street. And in this, we are basically using just the test segment and the 2 neighboring segments, the upstream sensor and the downstream segment. And with all these 3 sensors, we are basically fine-tuning our model rather than completely retraining our model to learn like what are the model weights, and that we are using for our prediction accuracy. For comparison models, what we did was that we used all the traditional models that we had. which is something like an ARIMA model, the random forest regression. So except the first one, all the three ones are classical machine learning models. Random forest regression or kernel ridge or support vector regression. And we wanted to complete that how well it's performing with this transfer learn. So in prediction windows, what we did for the domain data set, we had like 3 prediction windows. It can happen for any time of the day. So we are basically looking into like 15 minutes prediction, 30 minutes prediction, and 60 minutes prediction. So as the prediction window is increasing, we wanted to see that how well our model is performing. The GNCT, the transfer competition, had a different prediction window. So it was something like we have to predict whatever we are seeing up to like 6 a.m. We have to predict the next 4 hours or 3 hours. So it consists of basically just like from 1 minute prediction to up to like a 4 hours prediction. So something like for 6:05 a.m. we basically, it's just a 5-minute prediction window. But from 6 a.m. when we are looking for like 11 a.m. it's completely going to like 4 hours duration. So coming to the results, that how well that it performed. So what we basically saw is, so this is the basic heat map. So the x-axis is the time of the day, and the y-axis is basically the number of sensors. So we had like 15 sensors, and the first image that we have is the ground truth, and then we see that how well it's performing on the 15 minutes, 30 minutes, and the 60-minute prediction. And these are all in miles per hour. And what we can basically see is like, with 15 minutes duration, obviously, like since with the LSTM cell is basically taking into account just what is happening also in the recent past, that's why it also takes into account that, and thereby you can see all the regular congestion that has been taken into account. But obviously as we go like very long duration, so something like a 60 minutes, our prediction accuracy obviously increases. Means the accuracy is decreasing and the RMSE is increasing. That is expected because we have to predict for a much longer duration now compared to the 15 minutes or 30 minutes prediction. But the main thing is to see that how well it also performs on a snowy day. So this was like unexpected event that is happening. So we had a bad weather conditions, and that you can basically see that other than the recurring congestion that is around the morning peak, we have a completely different case of how it has performed over the evening peak when the snow has hit. And we basically wanted to see that how well it performs. Obviously, prediction accuracy, the RMSE value increases here compared to a normal weekday where we had like typically like 3 to 4 miles per hour as a prediction accuracy. Here we have a little bit higher, and it even goes to like a 8 miles per hour or something like that. That is expected because for a 60-minute duration, obviously we don't know that when the weather is going to hit or something like that. But this is to basically show that how well this model performs also on the different bad weather conditions that we have to take into account. So on a comparison algorithms, what we found that our model was almost similar, but also it was comparable to all the other models that we had. So ARIMA models didn't perform all well, but the other machine learning models also performed almost similar to what the LSTM model that we had. So this is with the normal weekday that we had, the prediction accuracy was something like just 3 miles per hour. But when it goes to something like a higher on a snowy weekday, we had a higher higher RMSE value, so something like 5 miles per hour to it goes to something like 8 miles per hour. But the results were comparable to classical machine learning models. That's what we see here. So coming to the Xi'an dataset, we basically first validated it on the last 3 days of the training data that we had. We used that as the validation data set, and in miles per hour, we saw something like just like 2 miles per hour error that we had. And finally, the accuracy that we saw here. So this is the final leaderboard that was just based on the accuracy values. And in just a quick, basically clarification that we were basically looking just into like forecasting models. So that's why we didn't take into account the first models or something like the traffic flow theory, which the first speaker covered, because that was basically something like the knife speed that was already described. So it's basically taking into what is happening on the other regions right at the same time to predict what is going to happen and that the test segment. But here we are considering is we don't have the information of what is happening on the other regions, and we have to completely predict or forecast it what is happening over the next 15 minutes rather than taking into right at that time what has happened on the neighboring segments to go into like what is going to happen in the unknown segment. So that's why we didn't include that in our model, but in the Des Moines data set, we basically included all the other models in our data sets. So coming to the conclusions, what we learned with our basic goal was to see that how well that it transfer learns. So with the basic model that we learned, we are basically transferring it and we just use, this was basically to avoid overfitting and the data hungry issues of the deep learning models. And we saw that it performed like quite well. And it basically shows that how well deep learning models can also perform with all this shifting of the weights and reusing the weights for a completely different location, which can be used for any other data set in completely different locations. And we were ranked 4th in terms of the accuracy of the RMSE and ultimately 5th. But also a very good extension that can be done is something like once we take into account the weather into considerations, we can basically have a much better forecasting, particularly when we go to like a long-term forecasting. So we are trying to use something like a weather information that can really help to have a much better long-term forecasting. So thank you, everyone. You can basically come in, get in touch with me in this email ID, and I'm free. Feel free to ask me any questions now. Thank you.
Perfect. Thank you so much, Dr. Pranamish. I appreciate the great presentation. Like I mentioned in the chat box, if you have any questions, please go ahead and send them. If you don't feel comfortable doing so, you can simply unmute yourself and ask your questions to the participants. I haven't received any questions so far, so I'm gonna give it a minute. And if I don't receive any, I have 3 questions actually. Okay, so I don't see anyone asking, so I'm gonna go ahead and ask my questions. And my first couple of questions are actually one question for presenter or for the first presentation, Dr. G, and that is about the RMSE. You showed 2 values, the 3.87, which was, I think, by the Arimax, and the other one was 7.72 for the neural networks, and you selected the neural networks. So I'm not sure which RMSE is the final one.
Let me share my slides here. So are you referring to, sorry, are you referring to these slides?
Yes, this one, and actually in the Arimax had a much lower, yeah, this one.
Oh yeah, okay. Yeah, so this RMSE is calculated based on the training set. It's just a training set RMSE.
Okay, okay, okay. So my second question is for the second presentation, and that is you selected only 5 time steps to go back and look at the correlation and so forth. Was that based on some sensitivity analysis, or that was some kind of, you know, you just selected it?
Basically, we started out with the single link predictions on 5 minutes, and that was actually trial and error. So basically, we tried to increase more, but if you increase more time steps, you basically increase the complexity of the model. So basically, it's a trade-off between efficiency and accuracy.
So basically, you did some sensitivity analysis.
Yeah.
Kind of. Okay. Okay. Perfect. Last question, and that is for a third presentation. And that was the RMSE. I think it's less than the one you used in the competition. Is that right?
So it's basically in miles per hour that we have. So that's why you are seeing a lesser value. But the final slide that I had, it was basically exact the same thing. But our entire presentation is basically on miles per hour, which was basically the main speed that we had when we are basically doing the demo and data set. But the final accuracy, the final slide that I had was the exact similar to what we had. So that's basically just showing the other teams, what they had achieved and what we have achieved.
Perfect, perfect. Okay. Any questions from the participants? Seems like I'm not receiving any. So I would just conclude the webinar today. I would like to thank the presenters and the participants for participating in this webinar and for the great presentations we've seen today. I just want to mention that this webinar is recorded and is going to be posted on our website, ABJ70 website. Once this is done, I'm going to notify everyone. Again, thank you very much, and looking forward to maybe meeting you or talking to you in the near future. Thank you so much.
Thank you.
Thank you.